This video covers material from section 3.3, Derivatives of Logarithmic Functions. In this section, we will learn how to take derivatives of logarithmic functions and learn a new derivative technique called logarithmic differentiation. Finally, we'll learn how to express this number e that we've been using. We'll learn how to express e as a limit. Before we get into taking derivatives of logarithmic functions, let's review a few of the properties of logs. So remember that the generic exponential function y equal a to the x, where a is any valid base, a has to be a positive number but not 1, that a has an inverse. It's a one-to-one function. Sorry, a to the x has an inverse. It's a one-to-one function. Its inverse is called the logarithm base a. So y equal log base a of x is the inverse of the exponential function y equal a to the x. Same thing if it was y equal e to the x, its inverse function would be y equal ln x. All right, now we can convert between exponential and logarithmic form, right? We can write y equal log base a of x. An equivalent expression in exponential form would be x equal a to the y. Or with the base e, y equal ln x, its equivalent exponential form is x equal e to the y. Right? These are equivalent expressions. We will see this in use when we walk through a proof of the derivative of ln x. And one last thing to mention, most of your calculators have a button called log and a button called ln. And just to remind you, the log on your calculators will mean log base 10, and ln will mean log base e. Now, if you go out and use some mathematical software packages like Mathematica or Maple or I don't know, maybe even Microsoft Excel, I'm not even sure, but but if you use something like, for example, Wolfram Alpha is a popular tool. It's based on some of the things in Mathematica. Wolfram Alpha, if you type log 5, it's not going to give you log base 10 of 5. It will give you ln 5. So be a little careful when you use software packages. Your calculators clearly say log is log base 10 and ln is log base e, right? They have two different buttons. But a lot of the software packages don't make that distinction, and if you want log base 10, you have to write it a special way. Or if you want log base 5, a lot of those packages will let you do that. But in many of them, if you just type log, it means ln. Okay, I'd also want to review a little bit of the properties of logs. We're going to need these when we take derivatives of logarithmic expressions, and in particular when we do logarithmic differentiation. So the three big ones that we need to make sure we're really comfortable with are the product, quotient, and power rules of logs. So these are valid for any base, and if I take the log of a product, log of x times y, the log of a product, the log of xy, is log x plus log y. So the log of a product is the sum of the logs. The log of a quotient, the log of x divided by y, log of x over y is log x minus log y. The log of a quotient is the difference of the logs. And then jumping down to the power rule, the log of the x to the y, the log of something raised to a power, the log of x to the y says I can take that y, that power y, and move it down in front of the logarithm, and log of x to the y becomes y times log x. So these three rules will allow us to simplify complicated logarithmic expressions and make, hopefully, the derivative process much easier once we get to that. Now, this reciprocal rule that I skipped over is really just a special case of the quotient rule, where that numerator function x is just the function, the number 1. And down at the bottom of the last bullet here, we see that log of 1 is always 0. So if I do the quotient rule on this, right, the log of a quotient is the difference of the logs. It'd be log 1 minus log y, or 0 minus log y, which is just minus log y. So not something that will come up too terribly often, but maybe a shortcut, save you a step of using the quotient rule if you remember that property. And another property that we're probably not going to use very often, but might come up, is the change of base formula. Right, I can convert between two different bases of logarithms. Most of the time we would say convert between log base 5 of x and want to write it in terms of log base 10 or log base e, so we could use our calculators. But I could just as equivalently convert between log base 10 to log base 7 if I some reason needed to. Excuse me. We also have, let's skip down here, right? We also have the ability to convert the base of the exponential, right? I can do a change of base for exponential, and I can write the function a to the x in terms of the base e, right? A to the x is e to the x ln a, and we saw that when we derived the derivative rule for a to the x in section 3.2. We wrote a to the x as e to the x ln a, and then used the chain rule to take its derivative. All right, the other properties on here, again, they're just going to be some things that will help us simplify expressions. Remember that a function and its inverse, when I compose them, which is what's being done on, what is this, bullets 6 and 7, I guess, right? When I compose a function with its inverse, they basically cancel each other out. So if I take log base a of x, and I do a to the log base a of x, right? I compose those two functions, then I get out just x. And if I do log base a of a to the x, I get out just x. So if it was log base a of a to the 5, the answer would be 5. If I do log base a of 3x minus 9, the answer would be 3x minus 9. Same thing with the e functions, right? The e bases, right? E to the ln x is just x, and ln of e to the x is just x. And if I take log base a of a, the answer is 1, and ln of e, the answer is 1. Kind of special cases of these properties. Again, things that will help us simplify some expressions later. Good things to keep in mind. The most important things on here are the product, quotient, and power rules. Okay, before we get into taking the logarithmic differentiation, right, we have to learn how to take derivatives of logarithmic functions in general. So I've gone ahead and stated them here for us. I'll prove the derivative of ln x in the next slide, but just going to state the derivative rules here for us. For any exponential function a to the x, right, its inverse function would be log base a of x, and they're both differentiable everywhere. A to the x is a one-to-one function that's always positive, and so I can take its derivative everywhere. Its inverse function will be differentiable everywhere in its domain. And for logarithmic functions, right, it has to be we have to take log of a positive quantity. Can't take log of 0, can't take log of negatives. So as long as it's possible, as long as it's positive, it's possible to take a derivative and evaluate a logarithmic expression. I've copied in the derivative rules for our exponential functions just for reference, but our two new rules are what's at the bottom here. So only two new rules in this section. Derivative of ln x is 1 over x, and I'll prove that on the next page. And the derivative of log base a of x is 1 over x ln a. Now, of course, they have chain rule counterparts, just like our exponential and all of our other rules had chain rule counterparts, right? We said the derivative of e to the x was e to the x. Its chain rule counterpart said the derivative of e to a function is e to the function times the derivative of the function. Well, the same will apply for our logarithmic functions. The derivative of ln x is 1 over x, so the derivative of ln of a function is 1 over the function times the derivative of the function. Derivative of log base a of x is 1 over x ln a, so the derivative of log base a of a function is 1 over the function ln a times the derivative of the function. The one we'll use most often is this one right here. The derivative of ln of a function is 1 over the function times the derivative of the function. Should be very familiar with that by the end of this section. The derivative of ln of a function is 1 over the function times the derivative of the function. All right, now I said I wanted to prove this rule to you, so I'm going to do this using two different methods. The first, we'll use the theorem from 3.2 that talked about taking the derivative of an inverse function. And so I want to take the derivative of f inverse x, where f inverse x is ln x. I want to learn how to do that. To use that theorem, I'm going to have to know what the original function was. And of course, if f inverse is ln x, then f is e to the x. And my theorem says if I want to take the derivative of f inverse, then I can find that by finding 1 over f prime and evaluating it at f inverse. And of course, if f of x is e to the x, then f prime is also e to the x. And so 1 over f prime evaluated at f inverse is 1 over e to the f inverse x. Right? Might look weird, but remember, if I ask you to find f prime of 3, it would be e to the 3, or f prime of 17, it would be e to the 17. So f prime of f inverse is just e to the f inverse. Now, I know what f inverse is. F inverse is ln x, so I can substitute that in its place. 1 over e to the ln x, and that property from the previous slide said that e to the ln x is just x. All right, derivative rule is proved. Derivative of ln x is 1 over x. Now, if you don't like this theorem, this derivative of an inverse function theorem, then I can prove this a different way. And to do this, I'm going to use implicit differentiation. We're going to write the function y equal ln x and try and take the derivative of that by first converting to exponential form, right? Y equal ln x, its equivalent exponential form is e to the y equal x, and then take the derivative of that. And now this again needs implicit differentiation. The derivative of e to a function is e to the function times the derivative of the function. And of course the derivative of x is 1. Solving for dy dx, I divide both sides by e to the y. And of course e to the y is just x. So there we go. The derivative of ln x is 1 over x. Derivative rule proved. Short, easy proofs. Hopefully you can follow along with these. They're just little 3-line proofs. Coming up in the next part, we'll make use of these new derivative rules and talk about logarithmic differentiation, and then we'll end with talking about e as a limit.